So section 8.2, we're going to finish up talking about these two-dimensional figures that are in the plane. And so what we're going to talk about here is what's called polygons. And so to define that, a polygon is a closed figure. What that means is there's no openings in it. So it's a closed figure in a plane determined by 3 or more line segments. So we could draw 1,000 examples here, but here's one with 3 sides. Okay, so it's closed, so all the sides join together. Here's one with 5 sides. There's nothing special about any of these. Here's another one, just having fun, drawing some closed figures like that. Anything that you can use straight edges and you can close around is a polygon. So a specific kind of polygon, if all the sides are equal, what is called is a regular polygon. So if you see the word regular, that is giving you some key information about the polygon. And we will use that key information in one of our problems that we'll get to. So I've just given you a little table here. You do not have to memorize all the names of the different polygons. I just gave that to you for reference when you're going through your homework. On the test, I will tell you how many sides it has, because I'm not interested in more trivia than we need to have on this test. I like to say dodecagon, so a polygon with 12 sides. It's just a fun word to say. So that's a little bit about polygons. So one of the interesting bits of trivia that we have about a triangle, which is a polygon with 3 sides, the prefix tri means 3. The sum of the angles of any triangle is, does anyone know that bit of trivia? Have you heard that before? No? Great. Well, then I get to enlighten you today. The sum of the angles of any triangle is 180 degrees. So the question that occurs is there a way that we can know that, or is that just something somebody made up and we're assuming to be true? So without going into too much detail, here's a picture that we can use to kind of demonstrate that the sum of the angles are 180 degrees. And the way it's done, I'm just going to sketch the outline. You're not going to be responsible to reproduce this. I'm just letting you know for fun information here. So here's my triangle with angle A, angle B, and angle C. And I want to know, can I show those add up to 180 degrees? Well, here's what I know, that A with the little apostrophe, B with the apostrophe, C with the apostrophe, they make a straight line. So I know that A plus A with the apostrophe plus B with the apostrophe plus C with the apostrophe is 180 degrees because they form a straight line. Then I could use my angle relationships, that B apostrophe is equal to B because they are vertical angles. From the last section, a little bit of trivia. Who can tell me what kind of angles C and C apostrophe are that makes those equal? Why are C and C with the apostrophe equal? What kind of angles are those? Well said. Good word. C apostrophe and C, they are corresponding angles. And then the same thing's true for A and A apostrophe. So there's A and there's A apostrophe. Again, they are corresponding angles. So just from the little bit of knowledge that we had from the previous section, we can show that because A with the apostrophe, B with the apostrophe, C with the apostrophe, they add up to 180 degrees. We see these equal relationships. What that means is the angles in the triangle A plus B plus C is 180 degrees. And that is just kind of the sketched out way that you could demonstrate the sum of the angles of a triangle are 180 degrees. So before we move on and look at other figures, and can we say the same type of thing for something with 4 sides and 5 sides and 6 sides? Is there some sort of relationship? We're going to do the same sort of thing that we just did there with unknown angle numbers. in a problem like example 1. Again, this is a problem I like to put on the test because it shows different angle relationships. So again, put a little asterisk by this, and when you're doing your homework, focus on this. What I want to know is, can we figure out the value of x? Okay, x is right here down at the bottom. And we're going to use that little bit of trivia that we just found out about the sum of the angles of a triangle to figure this out, as well as some other things. So the triangle is inside is the thing that ties everything together. And I've got the 3 angles of the triangle. Do we know, or can we figure out any of the angles of the triangle inside just from the information given? Okay, the top left one, great, is 48 degrees because these two things have to add up to 180. Everybody tracking with me on that, on why that one's 48? Because 132 plus 48 has to add up to 180 degrees. It's a straight line. Okay, great. We're off to the races. We know one of them. Can we figure out another one? This one? Yeah. That one definitely is 48, but that's unfortunately not going to help me as far as my triangle here is concerned. But you're totally completely right. But we can use that property of vertical angles for one of the angles in the triangle. Yeah, the 37 degree right here. This one's 37 because it's vertical with that one right there. They have to be the same. And now we can use the property of triangles. We know 2 of the angles in the triangle, so we can figure out this third angle. I'm just going to put a little question mark right there to figure that out, because now the sum of the angles of any triangle is 180 degrees. So what that means is the question mark that I don't know, plus the 48 degrees, plus the 37 degrees has to equal 180. And then you just throw that down in your calculator. Do a little arithmetic here. So I start off with 180 degrees, then I'm going to subtract the 37, then I'm going to subtract the 48, and I end up with, the question mark is 95. And I'm not going to try to write it in there and make it all messy, but if my question mark here is 95, then that means what's the value of x? What does that have to be? 95, because it's a vertical angle. So x right there is 95 degrees. So there's a problem right next door, exercise 1, super similar in concept. Again, you're going to use the triangle inside. I've already actually given you one of the angles of the triangle, and you're going to see if you can figure out x with that information. What's that? Okay, I'm going to let you talk me through it in just a minute. I'm going to give everybody about 30 more seconds to make whatever progress that what they've got here. All right, help me out. What do I need to do to figure out what x is? Okay, so just so that anybody watching on the recording, this is a vertical angle, I've been told. So that's 30 degrees. Fantastic. Totally correct. Okay, so again, just for the video, in case anybody's watching, this angle at the top of the triangle, I've been told, we can find because these three angles have to add up to 180. So I'm going to take the 180 and I'm going to subtract the 35, and that gives me, let's see, 145. Then I'm going to subtract the 30, and that gives me 115. So I'm going to squeeze it in right here. That means this angle right here is 115. So far, so good. So great. So we finished this off because these two right here have to add up to 180 degrees as well. Well said. So 115 plus x, that's these two angles, has to equal 180. And so then x is going to turn out to be 65 degrees. Well done. Anybody got a question on either of those before I turn the page? I guarantee you I'm going to put a problem like that on the test. So if you like that problem, then you're going to like it on the test. It's going to be no different. All right, I'm flipping the page. Okay, so then the question is asked, can we do the same sort of thing with other figures that we just did for the triangle? If a triangle is 180 degrees, the sum of the angles, what can I say for something with four sides? So I'm just going to draw like a little rectangle here. What about something with five sides? So I'll draw something with five sides, a pentagon, is what that's called. And we'll do six sides just because we're going to follow the pattern. Something with six sides called a hexagon. And so 1, 2, 3, 4, 5, 6. There we go. You can, or you can just watch along. What we're going to do is we're going to figure out if there's a pattern so that I can determine the sum of the angles on the inside of any figure. Okay, so if you want to, or if you're just going to, if you'll soak it in better just by watching, either way. So what we're going to do here is, I've got this figure right here. It has four sides. And what I can do is I can take a little meat cleaver and I can now divide it up into triangles. So I'm just going to draw a diagonal. When I draw that diagonal, how many triangles have I made inside that four-sided figure? 2. Okay, so I had 4 sides. That's 2 triangles. Each of those triangles is 180 degrees. So I have 2 times 180 degrees is equal to 360 degrees. So the sum of the angles in any sort of four-sided figure is 360 degrees. Okay, that seems fun. We're going to do the same thing for the 5-sided figure now. So I'm just going to pick one of the vertexes, and I'm going to draw some diagonals. So whoop, right there, and I'm going to connect to the dot right here. So my 5-sided figure, I've drawn 2 diagonals. How many triangles did I divide that 5-sided figure into? There's 1, 2, 3 of them. So there's 3 triangles. And we know that each triangle, because we demonstrated it on the previous page, we know each triangle is 180 degrees. So that's 3 times 180 degrees, which is, I think, 540 degrees. If I'm doing my multiplication okay. All right, we're going to do this one more time, and then I want you to look at this and see if you can tell me what the pattern is between the number of sides and how many triangles. You might be able to tell me now, but hang on, don't spoil the surprise. So I'm going to do the same thing with my 6-sided figure. I'm going to draw some diagonals there. So this figure has 6 sides. How many triangles did I divide it into? Okay, 1, 2, 3, 4. That's great. Again, each of those triangles has 180 degrees, so that's 4 times 180, and that is going to be, what, 720? So I'm not going to draw it, but let's just pretend I was able to draw a figure that had 10 sides. I'm not a good artist. You can already tell by the things that I've drawn. Okay. If you had to guess based on the pattern here, we had 4 sides, 2 triangles, 5 sides, 3 triangles, 6 sides, 4 triangles. How many triangles do you think I could divide a 10-sided figure up into? Yes. The pattern is what? Yep, the number minus 2. And so those 8 triangles each have 180 degrees. And so that's going to be, I don't know, let's see if I can do this, 1,440 degrees. Great. So the sum in general, I'm just now taking what you told me and I'm generalizing it. So you've done all the thinking. The sum of the measures of the interior angles of a polygon with n sides is given by this. You take the number of sides, n, minus 2 times 180 degrees. Okay, that's just what we did in each of those examples. So what I would like you to do is for exercise 2 right there, I've asked you, what's the sum of the interior angles of an octagon? Octagon, if you look on the previous page, has 8 sides. Okay, so an octagon has 8 sides, so I'm just going to write that down. And so the sum of the interior angles is this. It's 8 minus 2, or maybe you just wrote down 6, that's fine, times 180 degrees. And when you throw that down into your calculator, what's 6 times 180? 1080, is that what you said? Perfect. Great job. Now, in general, we don't know what any of the angles are, okay, unless we're told a bit of specific information, okay? And here, this next problem, I'm going to give you the specific information. In example 2, I'm going to work through this one with you. Example 2, I tell you that my hexagon, which is something with 5 sides, is a regular hexagon. On the previous page, what did I tell you what it means when a figure is a regular figure? All the sides and all the angles, told you all the sides are equal. What that means is the angles as well. Yes. Oh, perfect. Thanks for looking that up so that I didn't make a tragic mistake. Hexagon is 6. Pentagon is 5. It's too early. I need a little more caffeine. Okay, so given a regular hexagon, so I'm going to write that so I don't forget. Clearly, I've got some memory issues going on today. Okay, given a regular hexagon, all the sides, all the angles of a regular figure are equal. So because it's regular, I can now do a little more. So what we're going to do is first, we're going to find the sum of the interior angles. We already did it up in the example, but I'm just going to mention it again. So we've got 6 minus 2 times 180 degrees. And so that's 4 times 180, or 720 degrees. Now, because it's regular, I can do the B part. If I was not told it's regular, I could not do this part. Find the measure of an individual angle. Okay, we can do that. So I'm going to take that 720 degrees. And if I have a hexagon, let's see if I can draw something even approaching looking like a regular hexagon. So well, that's not too bad. Maybe the best hexagon I've ever drawn. Great. So if I know that all of these angles here add up to 720, but I also know these are equal, what can I do with the 720 to figure out one of them? Perfect. I'm just going to divide by 6. And when I divide that by 6, I think your calculator will tell you that that means each one is 120 degrees. So I'm going to just label one of them here 120 degrees. Then the last part of the problem says this. What's the measure of an exterior angle then? So what that means is if I take this side and I just kind of keep drawing it, what's the measure of this angle right here? That's an exterior angle. How'd you get that 60? Perfect. Well said. Excellent. Yes. This 120 and whatever this one is has to add up to 180. So we keep using that idea of supplementary angles over and over and over again. So that's where the 60 degrees comes from. Perfect. So what I would like you to do, I'm going to give you a minute or two. Exercise 3, I'd like you to do the same thing with a dodecagon. And you can look on the front page because I probably can't tell you from memory how many sides that is. Okay, so this figure has 12 sides. So the first part of the problem was what's the sum of the interior angles? So that is 12 minus 2 times 180. And that's 10 times 180. So I know, I couldn't believe it. I thought I'd have to go get a new piece of paper. But yes, I happened to get 12 sides on there. So good day to be me, I guess. All right, what's the measure of each individual angle? So I'm going to take that 1800 and I'm going to divide it by 12. And what does that turn out to be for each angle? 150? Did I hear right? Perfect, thank you. So that means down here, it doesn't matter which one I label, I'll just label this one, 150 degrees. And then the last part of the problem says, okay, now what I'd like you to do is extend the side, and we want to know what that exterior angle is. And what did you come up with for that exterior angle? Yeah, because they add up to 180. Great. Seems like you're catching on to the relationships. That makes me happy. Great job. Anybody got a question before I turn the page? You're doing good. I think you're through the worst of it. All right. So triangles are classified in two different ways. So I'm just going to tell you the classifications that you distinguish here. So if you have a triangle that all the angles are acute. So this top row right here, we're going to learn the classifications of triangles based on their angles. So if all the angles are acute angles, then what you have is an acute triangle. They all still add up to 180. That never changes for any triangle in a plane. Great question. If you have a triangle that has an obtuse angle, remember last time in the last section, an obtuse angle is bigger than 90 degrees, then you have an obtuse triangle. Math people are not always super creative. I'm saying they're not because it has an obtuse angle. They call it an obtuse triangle. So it's they didn't really get too creative with the names for the triangles. In the second row, they got a little more creative. The last one is if you have a right angle, it's called a right triangle. Okay, so in the second row, I had to look up the spelling because I'm a terrible speller. If you have two equal sides and two equal angles, so if you look at a figure and they put these little marks right there, those little marks are telling you that those sides are equal. You can see that on this picture. You can see it on the next picture. So if you're doing your homework and a picture is labeled like that, what they want you to do is take to the bank that whatever sides are labeled are equal. So you can use that. So if you have two sides equal, then you have what's called an isosceles, I-S-O-S-C-E-L-E-S, an isosceles triangle. Don't worry, I'm not going to make you spell that on the test. I'm going to give you some things. You're going to circle the word on that one. If I can't spell it, I'm not going to make you spell it. If you have three equal sides, if all the sides are the same, all the angles are the same, that's called equilateral. See, the math people really stepped up their game on the names here. And then the last one, my favorite one to say and spell, if there's no sides equal or there's no relationships, it's called a scalene triangle. I don't know who thought of that word, but it seems interesting. So that's just a little bit of triangle trivia, but as was asked, I'm going to repeat this because it was such a good question. All the angles, the sum of all the angles and every one of those triangles still add up to 180 degrees, so that that does not change. So the thing that we're going to kind of finish up our time with in this section is we're going to talk about figures that have equal angles and proportional sides. They are called similar figures. So kind of like a projection. So for instance, this isosceles triangle right here, this isosceles triangle is like an inch tall on my paper. But if we went up to the white or the screen and we measured it, it's what, maybe about a foot tall or maybe 6 inches. I don't know. I can barely see anything. I'm not wearing my glasses. So, but they have the same shape. They're just a different size. That's what it means to be similar figures. Okay, same shape, but different size. So in example 3, I've given you two pentagons. Okay, they look like a home plate in baseball. Okay, and they're similar. They're the same shape. They're just different sizes. And so what we can do when we know this is we can then figure out any missing sides. So on these two figures, I've got A, B, C, D, E, that pentagon, and then P, Q, R, S, T. So we know our alphabet right there. And so I've labeled some of the sides. So the top side on the smaller figure is 4. The top side on the bigger figure is Y. I don't know what that one is. The right side on the smaller one's X. The right side on the bigger one is 3. And then lastly, this angled side here at the bottom right is 3 on this figure, and it's 4.5 on this figure. So what we're going to do is we're going to use that information to figure out what we don't know. So for instance, the A part, I'm going to figure out side BC, meaning the side that's labeled X. Well, when you know you have two figures that are similar, what you can do is you can set up a nice proportion. So the way you do this is you are going to pick a relationship that you know. Do I have a side there that I know that side for both figures? I'm sorry? Is there a side that I know for both? What is it? Yeah, right here. DC and then SR. It's the corresponding side of both figures. So here's what I'm going to do. I'm going to set up a relationship. So I'm just going to do the work over here where I have a little bit of space. So I'm going to put 3 in the top over 4.5. So what I've done is I've put the smaller figure, its measure on the top, and the larger in the bottom. So you might say, hey, could I have put the 4.5 in the top and the 3 in the bottom? And the answer is going to be yes. I'm going to show you that just so that you can have full confidence that that is true. The only thing that matters when you're setting up your proportion is consistency. So if I'm going to find the length of BC, I don't know what BC is. It's X. What's the corresponding side in the bigger figure to the X? Don't be sorry. What did you say? I just didn't. I've got CB in the smaller figure. Perfect. The corresponding side over here is QR. Great. So when I set up my proportion, since on this one I put the smaller one in the top and the larger one in the bottom, I've got to put the smaller one in the top, the X, the larger one on the bottom, 3. You just have to be consistent. It doesn't matter where you put the smaller one or larger one. If you would have put the larger one in the top right here, then that just means in your other fraction, you're going to put the larger figures in the top and the smaller figure in the bottom. You just have to be consistent. Either way you did it, it's going to come out to be the same answer. Here's how you solve a proportion. You just multiply along the diagonals. So I'm going to multiply the 4.5 times the X. And then the other diagonal, I multiply the 3 times the 3, and I get 9. And then your calculator will tell you when you put this in, when you divide both sides by the 4.5, you end up with that the value of X is equal to 2. So X here is 2. So what I would like you to do, please, using this figure, is I'd like you to set up a proportion like I did, and I want you to figure out what Y is, this top side. So in case you're struggling, make a fraction out of the sides that you know, just like we did on the previous one. You can use the same 2 sides, 3 and 4.5, and then equals, and then set up a relationship between the side you're looking for. All right, I'm looking for y. I'm going to circle it. It's right here. What's the corresponding side in the smaller figure? Yeah, AB, which I'm told is 4. I'm going to circle it right there. So once again, I know these sides. These were given 3 right here, this side, and 4.5. They are related, 3 over 4.5. And now I'm going to make another fraction so I can figure out what y is. Where am I going to put the 4? Because according to how I have mine written, I've got the 3 from the smaller figure and the 4.5 from the larger figure. Where am I going to put the 4? Top or bottom? Smaller figure. And the y is part of the larger figure, so I put it in the bottom. Again, I'm just going to write this down in case you did it, because I want everybody to be fully confident. If you used the information you knew and had 4.5 over 3, then what you hopefully have is the y is on the top and the 4 is on the bottom. Okay? Again, it doesn't matter which way you do it. You just have to be consistent. And so then to solve the proportion, I'm going to multiply along the diagonals. So 3 times y is equal to 4.5 times 4, which is 18. Now I'm use my calculator. I'm going to divide both sides by 3. And then I have y is equal to 6. So the value of y up here is 6. So I'm going to flip the page. I've got a problem for you to do. Same sort of thing. 2 similar figures. So I'm going to give you a couple minutes. Go ahead and make your best attempt at finding what x and y is. And it all starts with noting what side on both figures do you know the measure of. That's gonna be your initial relationship. So just to get us started, I'm going to give you a little more time to work, but just in case you didn't quite see it. So what sides am I given? What's the fraction that I can make out of the sides that I know for both figures? Sure. So let's find x. 18 is from the smaller one over 22.5. That's from the larger one. Great. So then if I'm going to figure out what x is, what fraction am I going to make that's going to help me do that? I'm sorry, what'd you say? Yeah, why did you put the 16 in the top? You're 100% correct right there. So what you did, because you're the one that's giving me the answer, is you put the smaller one in the top and the larger one in the bottom. So then to find x, you put the smaller one in the top, larger one in the bottom. Great. Just consistency. So now we will solve this. We'll go along the diagonal. 18 times x is 18x. 16 times 22 and a half is something. Anyone's got that? Feel free to. 360, beautiful. And then when I divide both sides by 18, we get that x is going to be, it looks like that's going to be 20. Sure, what's up? But I did it like I used both sides at the same time. Right. So yeah, that's 100% correct. When I'm presenting something, I just try not to give too many alternatives because I don't want to. But what you've done, so in case you didn't hear the question, is instead of setting up the proportion using smaller to larger or larger to smaller, what he did is he said, okay, I'm going to set up the relationship this way. I'm going to do 18 over 16. Okay, these are the two sides. So he set up, can you see it on the screen? I got 18 over 16. So he did the left side over the bottom. And then over here, he did the same thing and took the left side, which is 22.5 over the bottom. That will work all the time. I just try not to give too many different alternatives because I don't want to conflate it in people's minds. But since you brought it up, awesome. Okay, so if anybody else did that, it's fine. Remember, the whole key in setting up your proportion is whatever you do, be consistent. Okay, so notice in his, he did left to bottom. So the other fraction has to be left to bottom as well. You couldn't flip it around and put the bottom in the numerator of the fraction. Okay, so when I did it, I did smaller to larger. So smaller to larger. So consistency is the thing that matters for the proportions. Okay, great question. Love it. Thank you for bringing that up. So then for the y problem, same sort of thing. I've got my 18. I'm going to do the work right here. I've got my 18 to the 22.5. (17 over y). Once again, same thing. Or if you did it as was just mentioned, you might have done 18 over 17 is equal to 22.5 over y. That will work as well. So now I'll cross multiply. So I've got the 18y is equal to 17 times 22.5. 382.5. Thanks for your help. Divide by 18. And what is that? All right, 21.25 is what the calculator tells me. Are we doing okay on these similar figures, the proportions? Okay, great. I'm hoping these things are nice and relaxing. So when I put a couple of them on the test, you're gonna feel great about it. Okay, so a specific type of similar figure. If I have two similar figures and the sides are all equal, what those are called is congruent. There's a lot less arithmetic to do in our congruent figures. So once you've written that down, I'm gonna do the first part of exercise 5, and then you're gonna do the other two parts. So here are my two congruent figures. I've got A, B, and C, and then I've got A with an apostrophe, B with apostrophe, C with the apostrophe. And so I know certain things. So what is B with the apostrophe, C with the apostrophe? So I want to know what's this side right here that I am tracing blue. Yep, it's the same thing as BC. They're congruent figures, so the sides are equal. So this is 18. No calculating that you have to do when you know that the figures are exactly the same. So just real quick, I'm going to give you 35 seconds. Do the B part and the C part. Figure out what those values are going to be, please. So the B part, I've asked you what is AB. So here is AB. I'm tracing it purple. And so what is AB? Yep, it's going to be the same thing as A with the apostrophe, B with the apostrophe. So it's going to be equal to 33. Perfect. And then the last one is what's the measure of angle A? Excuse me, A with the apostrophe. Yep, it's the same thing as the measure of angle A because they are congruent figures. So that is equal to 31 degrees. Perfection. Okay, so that there is the content for your test. I got one more thing I'm going to tell you to get you ready for the next unit. Our book just put this next little bit of trivia in this section, so I'm going to mention it. But are any questions? Anything that we need to go back over? Because you have a test on Thursday. So we're shown right here that the measure of A is 31 degrees. And so since they are congruent figures, meaning all the sides, all the angles are equal, then A is going to have that same value. All right, awesome. Great question. Appreciate you asking it. All right, so the last thing, when we come back next week after our test, we are going to talk a little bit more about polygons and finding the size of the interior region. And so one of the figures that we spend the most time on are quadrilaterals. Remember, quad means four, so four-sided figures. So this is going to be relevant and important when we come back next Tuesday when we start that section. So just keep this kind of in the back of your brain. So the different types of quadrilaterals that we are going to work with here, if you have a figure that has two sides parallel and the other two sides are not, so like this, in this figure, the top and the bottom are the same distance apart. The left and the right, you can see they go off at different angles. This is what's called a trapezoid. The next figure, both pairs of sides are parallel. So my top and my bottom are parallel, and my left and my right are also parallel. So what's nice about that is the top and the bottom side are equal, and the left and the right side are equal because of the parallel nature. And what that's called is a parallelogram. I can't talk and spell that, so hang on. I think I did it right. Parallelogram. So we gradually get a little more specific in some of these. So I'm just going to move downward. If you have a parallelogram, so top and bottom are parallel, left and right are parallel. If you have a parallelogram with this specific situation, you have right angles. Okay, so if you have right angles, that's called a rectangle. So a rectangle is just a specific type of parallelogram. Okay, so I'm just going to draw a little arrow. Okay, if you get a little more specific, you get what's called a rectangle. If I get specific in a different way, instead of right angles, if I have a parallelogram, so my top and bottom are parallel, my left and right are parallel, but now all the sides are equal. This is called a rhombus. So a rhombus is a special type of parallelogram, meaning everything is equal. So I'm going to put those little marks here so that you know. So it all starts with the parallelogram. A rectangle is a special kind of parallelogram with right angles. A rhombus is a special type of parallelogram with all the sides equal. And then if you do both of those things at the same time, if you do all the sides equal and you do right angles, you get the most specific type of parallelogram called a square.